Okay, so this is about principles of radiation. Okay, so we learned from our previous discussions that Earth observation remote sensing measures the electromagnetic energy emitted or reflected by the target or object. So let us recall what is electromagnetic energy. So we learned in physics that electromagnetic energy radiates or travels in accordance with the wave theory. That is, C is equal to V times lambda, wherein C is the velocity of light, V is the frequency, and lambda is the wavelength. Now, we also learned that when the electromagnetic energy interacts with a matter or object, it also follows the quantum theory, which is given by Q equals H times V. Q is the energy of a quantum measured in joules. H is the Planck's constant measured in joules second. And V is the frequency. Okay, so substituting the wave theory to the quantum theory equation, then we can simplify the equation into Q equals HC over lambda. Okay, so meaning to say the longer the wavelength, the lower is the energy content of the wave. This equations implies that as the lambda increases, the energy level or the energy content of the wave decreases. In remote sensing, this implies that sensing systems that operate in longer wavelength must operate larger areas of the Earth in order for the sensor to detect signals. Okay, so let me proceed with the electromagnetic spectrum. Electromagnetic spectrum is basically the collection of all range of electromagnetic radiation. Okay, so in remote sensing, we make use of the electromagnetic spectrum in order to determine which wavelength that is capable of sensing object or sensing matter. Okay, so as you can see, a spectrum is divided into several regions. We have the cosmic rays, gamma rays, X-rays, UV, the visible region, infrared region, microwave, and radio waves. Okay. Also, I would like to emphasize that remote sensing operates in three regions. One is the visible region, two is infrared region, and three is microwave region, wherein the visible region is further divided into three sub-regions such as blue, green, and red region. Blue has a wavelength of 0.4 to 0.5 micrometers. Green is around 0.5 to 0.6 micrometers. Red is 0.6 to 0.7 micrometers. Likewise, the infrared region is also divided into three. We have the near infrared region, the middle infrared region, and the thermal infrared region. In other books, the thermal infrared region is part of the far infrared region. That includes also the very long wave infrared region. Likewise, the microwave region is divided into several regions. We have K, X, C, S, and L. These are basically the radar bands. Okay, so we will not discuss it further. What are radar bands? Because there is a separate discussions about radar bands. Okay, so principles of radiations. We have the sun as a source of energy for remote sensing systems. However, we also know that objects that have temperature of above 0 Kelvin also emit energy, and that amount of energy is related to its surface temperature. And this is stated on the Stefan-Boltzmann law, which states that the amount of energy being radiated from the object is directly related to the 4 power of its surface temperature. In other words, the higher the temperature of the object, or the higher the temperature of the surface of the object, the higher is its energy existence. Okay, so this figure illustrates the Stefan-Boltzmann law, or it is the spectral distribution of energy radiated from black bodies at various temperature. So what is a black body? Black body is basically any object that has a temperature of above 0 Kelvin. Or in other words, black bodies are objects that have temperature of above 0 Kelvin. Okay, so this figure illustrates the amount of energy radiated from black bodies at different temperatures in relation to the wavelength. For example, you have for an object that has a 200 degrees Kelvin, its amount of energy is only around 5. And for 1000 Kelvin, its amount of energy radiated is 10 to the 4 power. And for 6000 Kelvin, or for an object that has a temperature of 6000 Kelvin, its amount of energy radiated is equal to or around 10 to the 8 power. Okay, so this illustrates, or this implies, that as the peak of the curve shifted to the shorter wavelength, the temperature also increases. Basically, or actually, this phenomena can be observed when we heat a metal or an iron. As the object becomes hotter and hotter, the metal glows to yellow and eventually turns to white. That phenomena can be explained through the principles of Stefan-Boltzmann law. Okay, so that is all about the principles of radiation. Our next discussion would be energy interactions in the atmosphere.